All right, everybody, welcome back to more Physics 11 notes. This is going to be the last section of notes for our first unit on kinematics in one dimension. So we're going to keep on talking about things that are accelerating, and in this lesson we're going to look at what happens when things are free falling. So if you drop an object or throw an object up in the air, and as it's going through the air, really only gravity is the thing that's working on it. That's what we call free fall. So now, a little bit surprising might be the fact that on Earth, if we ignore air resistance, everything free falls, everything accelerates at the same rate. So, in the absence of air friction, all objects accelerate at the same rate. Now, that might sound a little bit surprising because if you think to yourself, well, if I drop a feather and if I drop a hammer, those two things are not going to hit the ground at the same time. And you would be right. But the reason for that is not gravity. The reason for that is air resistance. The feather experiences a certain amount of air resistance, and that air resistance is a really big deal to the feather. But that amount of air resistance on a hammer doesn't really matter too much. There was a famous experiment done on the surface of the moon where an astronaut drops both a feather and a hammer, and you can see the two of them actually fall and hit the ground at the exact same time. So in Physics 11 land, we are going to just for the time being ignore air resistance. We know it's there, but it's really complicated to deal with. And so we're going to look at situations where air resistance is basically negligible. If you drop a golf ball or a bowling ball or a pumpkin, and you drop it 5 or 10 or even 15 meters, the amount of air resistance it experiences is not going to be all that much. So we can assume that it's basically negligible or zero. So near Earth's surface, the acceleration of all objects will be approximately negative 9.8 meters per second squared. Negative because it's downwards. And that 9.8 is an approximation. We'll actually learn a little bit later that even on the surface of the Earth, there are slight variations in that number. And of course, if you were to get further and further away from the Earth, that number would be different. But for right now, we can use that as an approximation. So whenever we have objects that are falling or being thrown up in the air, we can use that acceleration. So let's look at some examples. A student drops their homework down a well. And after 2.4 seconds, it hits the bottom, the water at the bottom. How deep is the well? So the first thing we're going to do with these problems, just like we always do, is we're just going to draw a little picture here so we can visualize what's happening. And so I've got my well with some water at the bottom, and I'm going to drop this homework down the well. Okay, and we're looking for how deep is the well. So I guess what we're looking for here is like how far does the homework fall before it hits the water. So I can set up my variables just like I always do. I've got V, V naught, A, D, and T. And at first glance, it doesn't look like I have much information here because they tell me that I drop the homework and 2.4 seconds later it hits the water. So I know that the homework is falling for 2.4 seconds, but it doesn't look like I have any more information. I need 3 variables in order to make these work. Well, as it happens, since it's falling, then I know its acceleration is going to be negative 9.8 meters per second squared if I ignore air resistance. And there's one other thing I know, because if I take the homework and I just drop it, I just let it go, in that first instant that it leaves my hand, the velocity would be 0. And so I actually have 3 variables I can work with. So picking a formula now that's going to involve initial velocity, acceleration, displacement, and time, I see that I've got this one here. D equals V naught T plus 1/2 AT squared. Now, normally we'd have to do some algebra and move some things around to solve, except this time it's already solved for D, and D is the thing I'm trying to find. So the first thing I actually am going to do is I'm just going to sub in this 0. Anytime you have a variable that is 0, go ahead and put it in your equation, just see what it does. Because if initial velocity is 0, then this whole thing is going to be 0. Because 0 times anything, it doesn't matter what time is, 0 times anything is going to be 0. So now I've got D equals 1/2 AT squared, and I'm going to sub in my variables. So 1/2 times negative 9.8 times 2.4, and then squared. Now, before you just go hammering stuff into your calculator, it's really good practice to think about what are you expecting from your answer. So looking at this picture here, the homework starts here and it falls down to there, falls down to this point right here. So I'm expecting, and changes color as it falls apparently, I'm expecting that the displacement should be negative. So when I put this in my calculator, I should get a negative number. 0.5 times negative 9.8 times 2.4 squared equals, and I get negative 28.24 meters. Negative 22 meters. Okay, I'm going to round that off to sig figs. I guess it's only 2 sig figs, so we'll just call it negative 28 meters. Or to answer the original question, the well is 28 meters deep. All right, so now we've got the next one here. Football is kicked straight up in the air. Now for these problems, when you're working along on them at home, I really highly recommend that you try it first. Now you might not be able to do the whole thing, but hit pause right now and just set it up. Draw the picture, set up your variables, and then see if you can find a formula that maybe will let you solve what you're looking for. And if you get stuck, that's fine. Just hit unpause, and then you can watch the solution. Okay, so here we go. So a football kicks straight up in the air at 15 meters per second. How high does it go, and what's its total hang time? How long is it in the air? So first thing, I'm going to draw a picture here. I've got a football, and I'm kicking it up in the air, and so it's going to go up. It's going straight up in the air like that. And I guess as it goes, it's going up some height. So I could call this D. It's got a certain displacement upwards. It's kicked up in the air at 15 meters per second. So right there, that's 15 meters per second. Okay. And so let's set up our variables and see where we get to. So I got V, V naught, A, D, T. And, well, 15 meters per second, that's my initial velocity. So that's going to be positive 15. I'm looking for the displacement, so that's something I want to know. And I guess if the football, even if the football is going up in the air, it's slowing down because of gravity. That's the acceleration due to gravity. So the acceleration is negative 9.8 meters per second squared. Now, I've only got 2 variables so far until I kind of consider the situation, which is the ball goes up in the air, slows down, stops, and then eventually comes back down. So the highest point it reaches, at that highest point, the velocity for like a split second, that final velocity must be 0, or else it would already be falling down, or it would still be going upwards. And so right at the very highest point, the final velocity is 0. Now I've got my 3 variables, and now I can work with that. So the formula that I can use would be this one: V squared equals V naught squared plus 2AD. Again, I said if you ever have 0, just put that in and see what that does. So V final is 0, so I'm just going to get rid of that. So that's now 0 equals V naught squared plus 2AD. And I need to solve for D. So I'm going to subtract V naught squared from both sides and get negative V naught squared equals 2AD. And then I'm going to divide by 2 and by A, both sides. And so I get this equation here. D is equal to negative V naught squared over 2 times A. And now I can put in my variables. So negative V initial is negative 15 squared over 2 times negative 9.8. Now, again, before you just go and throw this in your calculator, have a think about what kind of number you're expecting. And in particular, be really careful with your positive and negative signs. So I'm actually going to go look through here and see what this all means. This negative sign doesn't belong to this squared. The 15, positive 15 is squared, and then this is like times a negative 1 out front. So that negative 1 is not going to disappear because of the squared sign. However, I've got a negative sign on the bottom and a negative sign on top. And so when I divide a negative by a negative, they cancel and make a positive. So I'm just going to do that right now and make that a positive. I can see that this whole thing is going to give me a positive number, which makes sense because I kicked the ball up. So as it was going upwards, its displacement should be positive. And let's see what we get. So when I put this in my calculator, I'm just going to put 15 squared, and then I'm going to divide, but I have to put the bottom in brackets. If I don't have brackets, it's going to mess everything up. So 2 times 9.8, and then that is going to equal, we've got 11.48. Which I'm going to round off to just 2 sig figs. I'm going to call that 11 meters. Okay, so it goes 11 meters in the air. Nice. Now the next question is, what is the total hang time? Total hang time refers to the total amount of time that it is in the air. Well, I have my variables set up right now in such a way that I could find how long it takes for the ball to go up to the highest point. So maybe I'll go ahead and I'll find that and just see where that leads me. I'm going to use these exact same variables, but now I'm going to use this formula, v equals v naught plus at, and then I'll minus v naught, v minus v naught equals at, divide by a, so we get t equals v minus v naught over a, which is 0 minus 15 over negative 9.8. Now again, I can see here that 0, I should have got rid of that earlier on, should have taken my own advice. But anyways, that's not really going to change anything. Minus 15 divided by negative 9.8, those are both going to cancel. And so I'm going to end up with a positive answer, which is good because I don't know what to do with negative time. If you figure out what to do with negative time, let me know. We'll split the Nobel Prize, but me, I'm a little bit stumped. So 15 divided by 9.8 equals 1.531 seconds. Now think about what we just found there. What we just found was the time for the ball to go up to its highest point. If you throw something up in the air and as it goes up, gravity slows it down and it reaches a certain point, and then as it falls down, gravity speeds it back up again. The time that it takes to go up to the highest point is exactly equal to the time it takes to fall back down to that same height. And so really what I found was not the total time, but I found something called t1/2. So this whole time what I was finding there was t1/2, which is the halfway point. And so t total, you can imagine, is just equal to 2 times t1/2, which is 2 times 1.531, which I've got on my calculator here. And whenever possible, even though I wrote down a kind of a rounded off version there, I'm just going to use the full number in my calculator. I'm just going to multiply this by 2, and so I get 3.06. And so I get 3.06, which to 2 sig figs will just be 3.1 seconds. And there I go. Okay, all right, we're going to do one last example. Now again, I'm going to recommend, doesn't matter how far you can get, maybe you can just draw a picture. Maybe you can do a picture and a variable. Maybe you can do the whole thing. But hit pause and set up the problem, and then unpause and come back. I'll be waiting, and we'll do the full thing. Okay, so a student stands on the edge of a cliff, a very high cliff, okay, 45 meters, and they throw their physics homework straight up in the air. So it's a bad day to be physics homework. At 12 meters per second. How long does it take to come back down to the same height as the student? Okay, first step, draw a beautiful picture. Here's my student, not to scale, because they're a bit ginormous in this picture, but that's okay. So they throw their homework up in the air, goes up in the air, whee, then it comes back down, and it smashes on the ground over here. So that's kind of what we're looking at. I'm just going to write in what I know here. I know that the height of the cliff is 45 meters. That's impressive. They throw this up. So this gets thrown upwards here at 12 meters per second. Okay. Goes up and comes back down. Now there's 2 questions here, and they're slightly different. So you have to be careful about how we deal with them. The first question is, how long does it take to come back down to the same height as the student? So if I imagine a little imaginary line right here, how long does it take to go up and then come back down and be back at this point right here? How long will that take? So I'm going to set up my variables. I've got v naught, a, d, t. And let's see what we know. Well, the initial velocity is 12. Okay, so 12 meters per second. The acceleration is negative 9.8 meters per second squared. Now, something kind of funky happens here because the displacement, when it goes up and comes back down to the same height, the displacement is actually 0. Now, this is just a little bit weird. It's not wrong, but just some of your formulas, well, they get a little bit funky when the displacement is 0. So I'm actually going to find another variable. It's something else I actually know, which is, think about this. When you throw something up in the air, it goes up, gravity slows it down, stops it, and then from stopped, gravity speeds it back up in the downwards direction. What that means is, if there's no air resistance, when you throw something up in the air, if you catch it at the exact same height that it left your hand from, then the speed on the way up that it left your hand must be the same as the speed on the way down. Or the positive velocity that it left with must be the same as the negative velocity that it hit your hand with. So put another way, at this point right here, the velocity must be negative 12 meters per second. And so that's what I can use here. I can use negative 12 meters per second for my velocity. And now to find the time, I can use v equals v naught plus at. And I'm going to skip a few algebra steps here because hopefully we're starting to get kind of used to this. I'm just going to move v naught to the other side and get v minus v naught equals at. And then I'm going to divide by a to get v minus v naught over a equals t. Or just rewritten over here, t equals v minus v naught over a. And now I'll substitute in my values. I've got negative 12 minus positive 12 all divided by negative 9.8. Okay, well this is going to be a little bit tricky one. Now if you want, you can do what I said before and you can cancel out negative signs and so on if you're careful, but I'm actually going to do this one in my calculator and just see what it comes out as. So when I do this negative, remember that you need to use this little negative button here, not the minus sign. So this is negative 12, and then I'm going to subtract from that positive 12, and then I'm just going to hit enter, which is negative 24. I should have done that in my head. And now I'm going to divide that whole thing by negative 9.8, and so I get 2.449 seconds, which if I round off to, I guess, 3 sig figs, would be 2.45 seconds. So that's how long it takes to go up and then come back down to the same height. The next question is, okay, what if it falls all the way to the bottom of the cliff? So what if it goes up, comes all the way back down, then falls all the way down to the bottom of the cliff? How fast is it traveling? How fast is it going right here? And so, well, you need to think about that. I can't say exactly what it is, but I'm expecting that it's probably going to be falling faster than 12, right? It's going to be falling faster because it falls all that way down. Now I'm going to set up a new set of variables here. V naught, a, d, t. Because while some of the things are the same, some things now have changed because I'm all the way down here at the bottom of the cliff. So for example, my initial velocity is still 12 meters per second. That's the same. But my final velocity is, I don't know. I don't know what that is. My acceleration is still negative 9.8 meters per second squared, but my displacement is not 0 anymore. And that's a key point, because if it goes up in the air, comes all the way back down to the same height, and then falls further, the displacement means it's fallen down that cliff. So the displacement is not just 45 meters, but it's negative 45 because it fell down. And so with these three variables, I should be able to find my velocity. Just want to point out that in this formula, this is displacement, not distance. So it doesn't matter that the homework goes up and then comes back down. All that matters is where it starts and where it ends up. Okay, and so I'm going to find the final velocity using this formula. So v squared equals v naught squared plus 2ad. And I can do that. That's a fairly straight solve. I'm just going to square root this whole thing and get v is equal to the square root of v naught squared plus 2 times a times d. And so that's going to equal the square root of 12 squared plus 2 times negative 9.8 times negative 45. Now this is a good time as well to look at what's going on inside this square root here. For example, this is going to be squared, that's fine, but then this negative number times that negative number, those are going to cancel out. And I'm going to do that ahead of time, not in my calculator, because it'd be too easy to forget it and mess it up. So I'm going to plug this in and we'll see what we get. Okay, we got square root, second function, square root of, we're going to do 12 squared plus 2 times 9.8 times 45, and I'm going to close my bracket, and that looks good, and I hit enter, and I get 32.03 meters per second. Now, I both love and hate that number. That's a great number because it is faster than 12, because I knew it had to go faster than 12. It was already falling at 12 and then it fell more, so it had to be going faster than that. So that's faster than 12, but the big problem is that's not negative. When this hits the ground here, we're definitely expecting a negative velocity. It hit the ground going downwards. That's how hitting the ground works. So what I find is often students get to this point and they go, meh, I'll just stick a negative in there and see what happens. And I really caution you against that, because Sometimes you can get away with it, but a lot of times if it doesn't give you the sign you're expecting, it might be a hint that you've made a mistake in your earlier work. So we need to be able to justify where that negative sign comes from. And we actually can if we look back over what we did in our algebra. When I took the square root here, the square root of a number is not just another number. There's two options. The square root of 4 is not just 2, it's plus or minus 2, because either one of those squared gives me 4. So whenever I take the square root, the answer is plus or minus that number, which means my answer here is plus or minus 32. And now this is where it's up to you to look at the situation and say, well, is it plus? Is it minus? Is it actually both, or is it neither? Because depending on the situation, you might reject one or two or none of those answers. So in this case, I'm going to reject the positive and say, no, it's just negative 32.0 meters per second. I know it's not going to be the positive one. Okay, that's it for Unit 1.